In this lesson, we are going to be working with properties of exponents to be able to simplify radicals and to simplify rational exponents. We will also be doing some division and multiplication. Let's start with a couple of questions. You must ask yourself, do I have the same base? Because when you have the same base, you'll be able to work with your exponents. And what we need to also ask is, do I have the same index? And if that's the case, then you'll be able to work with the bases. Let's take a look at a couple of examples. So if I want to simplify 3 to the 1/2 power times 3 to the 3/2 power, we have the same base. And since we're multiplying bases, we know from the properties of exponents that we then can add our exponents together. So that's going to equal 3 to the 4/2 power, because remember, when you add fractions you keep the denominator and we add the numerators. So if we simplify 4/2 as we simplify fractions, this is going to be 3 to the 2nd power, and 3 to the 2nd power is 9. If we take a look at the next example using our properties of exponents, our base is 4. Our exponent is 3/2, and it's raised to another power, which is 2. So that's going to be 2/1. So remember, what we can do with our fractions is we can multiply them. So when we multiply the numerators and the denominators. This is going to be 6/2. 6/2 as a fraction simplifies to 3, and 4 then to the 3rd power would be 64. In the next example, we could do this two ways. We could take 9 to the 1/2 power and 4 to the 1/2 power. And if you remember, when you take something to the 1/2 power, that's going to be the root, the square root. So we have the square root of 9 times the square root of 4. The square root of 9 is 3, and the square root of 4 is 2, and then we can multiply them together to get 6. Or we can do it this way. We can multiply 9 times 4, which is 36, and then 36 to the 1/2 power simply means the square root of 36, and the square root of 36 is 6. So you can see that there are a couple of different ways to work out that one. In the next example, we remember that when we have a negative exponent, that means we are going to take the reciprocal of the base, so that's going to be 1/25, and then to the 1/2 power. The 1/2 power means that we're taking the square root of 25. So that's going to leave us, as we simplify it, as 1/5. In the next example, when we are dividing like bases, remember that we subtract the exponents. So we have 5/2, and we're going to subtract 1/2. That's going to leave us with a base of 6. Remember, we keep the denominators and we subtract the numerators. That's going to be 4/2, which simplifies to 2, and 6 to the 2nd power is 36. In the next example, when we have a fraction raised to an exponent, we can simplify that by doing the numerator and denominator separately. And when it is to the 1/3 power, we remember that that simply means that that's the cubic root. So we have the cubic root of 8 and the cubic root of 27. So the 3rd root of 8 is 2, and the 3rd root of 27 is 3. So the answer will be 2/3. A couple of things for us to remember are that when we're dealing with rational exponents, we need to put them in simplest form. There will be no perfect nths, no negative exponents, and there will be no rational exponents in the numerator and the denominator. So let's take a look at an example. For example, if we have 1/7 to the 1/3 power, we remember that that means that that's going to be 1/the 3rd root of 7. We need to rationalize the denominator because we cannot have a root in the denominator. This is going to be a little bit different than rationalizing a denominator where it's a square root. because what we're looking for is what can I multiply so that I will get rid of the third root of 7. Well, I have only one 7 in the denominator, and if I want to get rid of a third root, I need a group of 3 7s. So what I'm going to do is multiply both the top and the bottom by the third root of 7 squared, or in other words, I want 2 more 7s. So in the numerator, I also must multiply by the third root of 7 squared. In other words, I'm going to multiply by 49, but it will help us to keep these in prime factorization. So now in the denominator I have the third root of, and I have 1 7 and 2 more 7s, which would be 7 cubed, or a group of 3 7s. And in the numerator I have the third root of 7 squared. So what we have in the denominator is the third root, and the exponent of 3 will cancel, so that leaves us with just a 7 in the denominator. And in the numerator, we can write this as the cube root of 7 squared, which is 49, or we could rewrite it as 7 to the 2/3 power over 7. Either way will be fine. Let's take a look at some more examples. So we want to simplify. 6 to the 1/2 power times 6 to the 1/3 power. Again, we have the same base, so we can add the exponents. We have 1/2 plus 1/3. These will be fractions that we want to add together. So we want to have a common denominator of 6. So 1/2 is simply 3 over 6, and 1/3 is simply 2 over 6. So this is going to give us 6 to the 5/6 power. Now in the next example, we have 25 to the 1/5 and 25 to the 2/5 in the numerator. So we're going to keep the base, and we are going to add the exponents together, which is going to give us 3/5. And in the denominator, I have 5 to the 3/5 power. What we talked about in the previous slide is that if you have the same index, which means the same exponent, we can work with the bases. So since we have the same exponent, we are able to divide the bases. So 25 divided by 5 is 5, and then that's going to be 5 to the 3/5 power, which means the exponent stays the same. In the next example, we have 4 to the 3rd power, and we have 2 to the 3rd power. Again, since the exponent is the same, we can work with the bases. 4 times 2 is 8, and that's going to be to the 3rd power. And then we're going to raise that to the negative 1/3 power. When we have a power raised to a power, we are going to multiply the exponents together. So we keep the base, and when we multiply the exponents, 3 over 1 times negative 1 over 3, that gives us a negative 1 power. And we also want to make sure that we have positive exponents, so when we do have a negative exponent, it tells us to take the reciprocal of the base, and then our exponent becomes positive. So our final answer would be 1 over 8. In our next example, we want to simplify. So we have 6, and we have 6 to the 3/4 power. Well, we have like bases, so what we can do is subtract the exponents. Well, this is to the 1st power, but if I want 1 to have a denominator of 4, we could rewrite that as 4 over 4. So I'm keeping the base, and then I'm going to subtract the exponents. So I have 4 over 4, and I'm going to subtract 3 over 4. So that's going to equal 6 to the 1/4 power. In the last example on this page, what we are going to do is we are going to simplify, and there's more than one way to do this. So what we could do first is to do each of these to the 3rd power, which means we're going to multiply the exponents together. So what I'm going to do is I have 18, and then 1/4 times 3 over 1 would be to the 3/4 power. And then I have 9 to the 3/4 power when I multiply the exponents, doing numerator and denominator separately. Now because the exponents are the same, we can work with the bases. we are dividing the bases. 18 divided by 9 is 2, and then we have our same exponent, which is to the 3/4 power. And that's working with simplifying rational exponents. Let's take a look and make sure we remember some properties of radicals. So the product property says that we can either multiply the two numbers together and then take the root, or we can take the root of each of them separately and then multiply them together. The same thing happens with the quotient property. We can divide and then take the radical or the root of them, or we can take the root of the numerator, the root of the denominator, and then divide. Please remember that we want to put the radicals in simplest form, which means there are no perfect nth powers under the radical, we don't leave fractions under the radical, and there are no radicals in the denominators of our fractions. So let's take a look at some examples that have radicals. So in the first example, we have 3, the root of 3 to 25, and the cubic root of 5. So if we remember using prime factorization that 25 is 5 times 5, which would be 5 squared, and then we have another 5, this means we would have the cube root of 3 5s, which is 5 to the 3rd power. These are opposite operations, the cube root and the power of 3, so if we simplify, this will just be 5. In the next example, because we have the exact same radical, which is the cubic root, we can divide first. So 32 divided by 4 will be 8, and so we want to find the cube root of 8. And if we do a prime factorization, we know that that would be 2 times 2 times 2, so the cube root would be 2. In our next example, we have the 4th root of 64. If we do the prime factorization for 64, we'd have 8 times 8, we'd have 4 times 2 and 2 times 2. Again, we'd have 4 times 2 and 2 times 2. And so we have 6 2's. So what we know is that we have a group of 4 2's, so that can come out of the radical. And then underneath the radical, we have 2 2's left. So we can simplify that by using our rational exponents. So this actually would be 2 to the 2 over 4 power, which is actually 2 to the 1/2 power. And if that's 2 to the 1/2 power, we can rewrite that as simply the square root of 2. So our final answer would be 2 square roots of 2. In the next example, we have the 4th root of 7 and the 4th root of 8. So what we want to do is to simplify that. We're going to rewrite these as our separate roots, numerator and denominator. If we were to do the prime factorization of 8, we'd have 4 times 2 and 2 times 2. So this is really 2 to the 3rd power. We would like to rationalize the denominator. We do not want a radical in the denominator. And I already have 3 2's under the radical. I need a group of 4 to be able to simplify. So all that I need to do then is to multiply both the numerator and the denominator by the 4th root of 2. What happens then is in the denominator, I have the 4th root of 1, 2, 3, 4 2's, so 2 to the 4th power. In the numerator, I am going to have the 4th root of, and since I have a root of 7 and 2, I can multiply those together to get the 4th root of 14. And when I finish simplifying the numerator as the 4th root of 14, the denominator, we have a 4th root and a power of 4. Those are opposites, so cancel each other, and so we simply have a 2 in the denominator. In our last set of examples, we are going to do some more simplifying. The square root of 4/9, we can simplify both of those and take the root separately. The square root of 4 is 2. And the square root of 9 is 3. In the next example, we can simplify because all of these are underneath the radical. I'm going to simplify and divide 15 by 5, which leaves me a root of 3, and simplify 10 by 5, which leaves me a root of 2. Well, then I still have a root of 3 and a root of 21, so I'm going to divide each of these by root of 3. Now I have my root of 2 and root of 7, and since they're both square roots, I can multiply them together, which would be 14. And I have a root of 1, and the square root of 1 is 1, so my final answer will be 14. In the next example, I know that the 196 is 14 times 14. And so if we take a look, I have the cube root of, and I have 1, 2, 3 14s when I do my prime factorization, and I could continue breaking that down, but I have a group of 3 14s, and the cube root of a cube root and a power of 3 are opposites of each other, so they cancel, and we're left with 14 as our simplified form. In the next example, since we have the square root of 27 divided by the square root of 3, I can simplify, which means I can divide first, and that gives me the square root of 9, and then I can simplify. The square root of 9 is 3. In the last example, if I'm multiplying my like roots together, I have the square root of 5 times the square root of 2, and since they're both radicals, I can multiply them together, and that gives me the square root of 10. So let's review. Please remember that we do not have any perfect nths when we are dealing with rational exponents. There are no negative exponents, and we do not want rational exponents in the numerator and the denominator. Radicals in simplest form, there are no perfect nth powers under the radical, no fractions under the radical, which means no radicals in the denominator. We need to rationalize the denominator. Please remember also the properties of radicals, the product property and the quotient property.